Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Colin Orion Chandler with us today. Hello, Colin.
Hello, how's it going?
I'm doing really awesome on this April 18th of 2024 as we record this. And Colin, what's your geolocation? Where are you at?
I am currently at University of Washington in Seattle right now.
Very cool. Has spring arrived?
It has definitely arrived. It's
Very
like over
nice.
60 degrees today, so it's t-shirt time.
Hey, we have evidence.
That's right.
I'm in Phoenix, and we are definitely hitting what I would call our mid to late spring form. So we kind of got up over 90 today. So yeah, we're approaching the triple digits. So it's all really cool. Very cool. And Colin, what do you like to do for research?
So I primarily focus on solar system science. I work especially in unusual active bodies. So this includes things like asteroids that surprisingly have comet tails,
Yes,
which is the subject of our work today.
very nice.
I'm also I'm a project scientist for the LSST Interdisciplinary Network for Collaboration Computing. So I'm also working on preparations for the Rarity-Rubin Legacy Survey of Space and
Yeah,
Time.
that'll be very exciting. Very cool. Very cool. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. The Active Asteroids Citizen Science Program Overview and First Results. And Colin, take us away.
Right. Well, thank you very much for that. I think the first thing I will do is shout out to my co-authors, especially Chad, Will, and Jay, and all the folks that were at NEU, where I did a lot of this work and where a lot of the computation still takes place. That's Northern Arizona University. Also, a special shout out to a number of the citizen scientist co-authors that are on this list.
Nice.
We can't do this project without them, and we're very happy about that. So,
very cool.
Yeah, so let's stroll on down into the abstract and we can get moseying in.
Okay.
I think the key takeaway is that we have a project that launched in 2021, and that we've made a bunch of discoveries. It's a NASA partner program hosted on the Universe platform, and you can visit activeasteroids.net to participate. It is an ongoing program. We've
Universe. Okay.
Yes, that's the key bit there. We have these numbers are here. If I say any other numbers today that are different from these in terms of number of volunteers, it's because it is an ongoing program, and we do have even more volunteers. So actually, it says that we've had 8,300 volunteers, but we're actually well above 10,000 volunteers at this point.
Very cool.
And about 620,000 images and about 8.3 million classifications as well.
Nice.
So there's some updated numbers I might refer to throughout.
Okay.
Yeah. So I think the key piece from the abstract is just that we've made these discoveries. I think we can skip the rest of it because we'll be hitting it on in a paper anyway.
Okay.
And so there's the main background that's important to understand is our motivation here is stemming from volatiles and understanding volatiles in the solar system.
Okay.
And so traditionally these were thought to be just from comets, and that comets delivered water to Earth, etc. We now know that it's a little bit more complicated than that. And also we know that bodies other than comets are active. So we mentioned here that in 1949, there was a comet Wilson-Harrington, which also got an asteroid number of 4015, was shown to be active. And so then in the intervening time span, a bunch more of these active asteroids have been found.
Okay.
Near Earth objects, as well as asteroids that orbit exclusively within the main asteroid belt.
Okay.
There are other mechanisms that can cause things to be active aside from sublimation, which we mentioned here too, and these are also interesting astrophysically. So things could be rotating faster and faster to the point where they become unstable and they start breaking up. And it's also possible for things to get too close to the sun and actually have thermal fracture take place, like the Geminid meteor stream parent 3200 Phaeton. And so there's different ways you can actually get a comet tail. But our underlying motivation is to understand volatiles, where they are in the solar system, how they got here on Earth, and of course these have implications for understanding how the prerequisites for life and other areas too.
Cool. I'm with.
Um, we mentioned a few times right here main belt comets. So this is a subset of active asteroid. These exclusively orbit within the main asteroid belt, and they have activity that is due to sublimation of volatiles.
Oh,
So
yeah.
that's there's very few of these objects are quite rare. And the fact that a lot of these populations are quite rare is going to be a recurring theme that we'll talk about. Even the comets themselves, there's just a few thousand out of like the 1.3 million known minor planets in the solar system.
Rare.
So we have to talk about these centaurs. So centaurs are thought to be bodies that originated in the Kuiper belt and have migrated inwards. They orbit between the orbits of Jupiter and Neptune, and so they're sort of a special class. They've also been known actually even longer than Wilson-Harrington in terms of activity. So we know they're active centaurs, starting with this Schwarzman-Wachmann 1 in 1927. But they're also pretty rare. I mean, just basically 20 active centaurs have been found in the intervening century, basically.
Yeah, 1927.
And so, yeah, once again, it's kind of hard to make a lot of broad claims about the population when we have so few of these numbers in terms of active centaurs.
Yeah, wow. Okay.
So there's other populations we'll talk about. There's one that's sort of a less well-known one called a quasi-Hilda object, quasi-Hilda asteroids, quasi-Hilda comets. Take your pick on the nomenclature.
Yeah.
These are bodies that have orbits that are similar to the archetype Hilda asteroid, the Hilda itself. Those are in stable interior 3-2 mean motion resonance with Jupiter. Quasi-Hildas are not. They're on orbits that are similar to Hilda, but they also share features with the Jupiter family comets, which are another population we talk about a bit. And these are comets generally with shorter periods that are out there.
Okay. Wow.
So we talk about the numbers. So about 3,000 quasi-Hildas identified through a couple different means. Those are the key players there, top 2006, and Gohanton and Megani in 2016. However, with again small numbers, that whole population, we got fewer than 15 active objects known.
Okay. Wow. Be nice to make those a little bit larger, wouldn't it?
Yeah, it sure would. So that's the key takeaway from all of these populations. We really would like to find more of them. You may have noticed that the project is called Active Asteroids. So we really set out with active asteroids in mind, but we also knew that we would find other active bodies, and we were excited about that prospect too.
Yes. Serendipitous discovery.
Yeah, absolutely. And so we'll talk about that exactly. It is all serendipitous discovery for us in terms of we're working with archival data. So that's what the next piece is this pipeline that called Harvest that does cutouts from. It works with other data sets, but for now we're working exclusively with the dark energy camera data. So this is on the Blanco 4-meter telescope at Cerro Tololo Inter-American Observatory in Chile.
Yep.
It's a fantastic instrument, really high quality data, and we use the community pipeline data as well. And so it's got really excellent astrometry and everything already built in.
Nice.
And so we have a proof of concept that we started with in 2018 that was designed to show that dark energy camera was suitable for finding active objects. I think actually if we want to skip down to figure 1, there's an image that's from that proof of concept.
Let's take a look at figure 1. Ooh, and here we go. Deck cam.
Oh, yeah. Yep, there we go. Yeah, so this is actually one of the images from that very first proof of concept. And so this object, believe it or not, actually does have a tail. It's roughly oriented towards the 6:30, 7 o'clock direction. It's very faint.
Yeah, very faint, but yeah.
It's definitely real, and there were follow-up observations at the time. That we did not discover this, but this was found in our data set. So we showed that it was definitely viable for the purpose of discovering activity. And this is what a typical thumbnail looks like. And we'll revisit this a couple more times. So maybe we'll hop back up to where we were in the harvest section.
Okay, let's go back up to harvest. We were at harvest. Here we go, harvest.
Yeah, so there we go. I mean, harvest is an acronym. I think it's hunting for activity in repositories with vetting enhanced search techniques. This is really just an internal pipeline. That
Mhm.
Safari paper, which also comes up throughout, that searching asteroids for activity revealing indicators. That's was the proof of concept paper from 2018. So
Cool.
the pipeline is harvest. That's what we keep referring to here.
Okay.
And so its main job is to cut out images from the dark energy camera centered on known minor planets. That is its primary job. But there's a lot of interim pieces, and so we'll just really briefly describe how that works here. We collect metadata from the different astronomical archives that back in the day was NORLab, and now it's Astro Archive.
Yeah.
So that's what's hosting all the metadata for DECCAM. We collect this data, we put it into a database. It's got useful stuff like when the observation happened and who the PI was, etc.
Good.
And we also want to do things like throw out some data that's definitely not going to be helpful for finding activity, like if it's right next to a full moon, for example, we know it's not going to be helpful. And we'll keep revisiting this whole vetting concept as we go. So yeah, that we collect and goes into this database. I think if you want to scroll down a little bit further. Yeah, I think that's the gist of it. The important piece for how we figure out what's actually in the field is that we use the INCZE Skybot service. So this is a service
Okay.
that lets it basically, you say, here's my pointing, what is in this field of view in terms of solar system objects, and it gives you a list of results, and that's how we figure out what's in there.
Yeah.
So yeah, let's keep moving on down there. So
Okay.
these catalog queries, in addition to Astro Archive and stuff, we also query JPL Horizons and
Nice.
the CADC. They're that's a Canadian Astronomical Data Center, and several others for both the observational records as well as for other properties about the objects, like semi-major axis and things that we need to do to compute some stuff later.
Cool.
We talked about those classes of object earlier, and so kind of along the way, we want to make sure that we keep track of the classifications for the different objects.
Yes.
And so that all facilitates that process right there. We talk about some exclusions again right here, and this is a recurring theme, especially when we talk about the scalability of this project in the future. But we do exclude observations that are, like I said earlier, close to the sun, or if they're the air mass is just it's above 3, and there's
Oh yeah.
these are specifically designed because we want to be able to see comet tails, and if things are not in the right set of conditions, the odds of seeing it are low. And as you know, spoiler alert, there's a lot of data, and so we from the beginning knew that we needed to stay on top of that and keep the best data for volunteers. So new data handling, we estimate the magnitude, the depth of each of these exposures for all of the archives that we consider. And the main point of this is so we can figure out if we can actually see the object or not. And if we can see it, do we have any chance of seeing a tail? And the tails tend to be fainter than the nucleus of the object in the image.
Okay.
In the same part of the pipeline, we also choose the one version of the image. So a lot of these community pipelines give you multiple versions as an option. So they may have, for DECCAM, they have something called Instacal, and they also have resampled. For us, Instacal works better. It doesn't have any sort of kerneling done, and so that's what we go with. But even there can be multiple versions sometimes. So we need to reduce duplication. We keep just one of everything.
Okay.
That's the goal.
Okay.
Yeah.
Cross fingers.
Yeah. And I know I mentioned JPL Horizons, but we also maintain the database of object data, and we'll revisit that in a minute.
Yes.
So then, yeah, so that's the source of object parameters, the object classification. So that we pull these in from other sources, including Skybot. They provide what they classify objects as, like as a main belt asteroid, or if it's an NEO, what kind of NEO it is, that's the near Earth object. And so we keep all of that even if we may reclassify stuff ourselves later, which we talk about, it's a really helpful initial starting point for working with the data.
Yeah. Okay.
Yeah, so we keep track of all of that.
Nice.
And we talked briefly here about some of the classic ways of classifying the data through different means. There's one called histogram parameter with respect to Jupiter. This describes like a body's level of influence by Jupiter, their orbit, I should say. And so there's some classic definitions of how you put objects in different boxes based on some of these parameters. So we'll revisit that as we get to the actual classification of the bodies.
Okay.
The point is that it's happening during this pipeline.
Yes. And you're gathering all that. Yep.
So next up is field analysis in the pipeline, and so this is using this is the stage where that Skybot procedure takes place, where we find out what's in there and where we actually do the calculations of what we call delta magnitude.
Okay.
And so we all know astronomers think Hipparcos, so that this negative numbers are brighter, and so we want things to be more negative if possible. So this is taking the apparent V-band magnitude that's provided by the JPL Horizons ephemeris service. That's kind of our standard.
Right.
And then we have a magnitude that's been achieved for this exposure using an integration time calculator. So this is a theoretical limit based on noise, etc., rather than a direct measurement. But this is still taking place before we've actually downloaded any data. We want to be able to do as much as we can without having to download a ton of data first.
Yes.
And so if we do offset for the color, so if we only have ephemeris for V-band, and so we offset for color for different filters to try to make it reasonable. These are not at all something that would be great for photometry, but for our purpose of filtering out data to see if we can reasonably expect to see an object. For example, if our exposure time calculator says we can only see something like 20 magnitude, and the object is reported by JPL to be at 26th magnitude or 30th magnitude, we know we're not really going to be able to see the object.
Get it. Yep.
Yeah. Okay. We do also at this same stage, we calculate the trail length. So this is just based on the apparent motion on sky as seen from Earth of the asteroid. Okay. So the longer the exposure, the longer the trail. For things like the asteroid belt, but also if things are really close, like NEOs or Mars crossing objects, they can have a very long trail even in a shorter exposure.
Okay.
And a trail for something that we're showing at the middle has the appearance of a tail, and so we do keep that in our hat later for being able to filter out objects. So we basically do not show people images that have trails that are longer than 15 pixels as a general policy. We started out with it early on, but people were thinking that they were tails, and so we just specify that right here. That's our modern cutoff limit for that. So the next stage of the pipeline is the thumbnail preparation. So here we are actually downloading data from Noir Labs, Astro Archive, or for other archives as well. Again, we only are using DECAM data currently for our projects. We download that data, we figure out where the corners are for all those chips, and we cut out the thumbnails for everything. So we have, these are 480 by 480 thumbnails with the object that's at the center, just like that figure one we saw earlier.
Right.
And so so these are all known objects, just to re-clarify. And so that's how we know where it is, and so it should be at the center. Now, if something is off by a bit, maybe a little bit off center, that's been pointed out before, that's fine. It happens because the orbit needs to be improved, etc.
Okay, cool. I'm with you.
And so, as we extract these thumbnails, so we make FITS cutouts, like our standard astronomy ones, but we also do PNG images. So like for Zooniverse, for the we're getting ahead of ourselves, assuming we're going to do this in science. Spoiler alert, it was kind of in the title.
We'll get there. We'll get
there. Yeah. We want to have this is a format that's much faster to load in a web page, and it already, for us, we have a predefined image enhancement for contrast stretching that we can apply. That makes it so that people have the best chance of actually seeing something if it's there.
Right. Okay.
And so that's what we produce in this stage.
Okay. Thumbnails.
Yeah, so we do some analysis of the thumbnails at this stage. This is of course on the fits thumbnails, but we're using source extractor
Right.
and checking to see a few things. The first one, and again, the reason for this is because we know there's going to be way too many of these images for us to look through.
Okay.
But we, for example, don't want to look at images
Yikes.
that don't have anything in the middle. So if
Yikes.
there's nothing to see,
Mm-hmm.
why bother? Also, if there's just a ton of stuff in the middle, if there's like 12 things overlapping, how are you going to tell which one is the object?
Right. Got it.
Too confusing. And if there's the same, if the entire field is just teeming with dots, basically,
Yeah.
it's too much still. So yeah, we're gonna hold off on those as well. So we describe some of these cuts that are right here.
Okay.
And we do a bunch of counting right at this stage. And this is for different metrics, which we describe later. But this helps us pick what we are going to send down the pipeline for the program.
Section. Uh-huh.
And yeah, the reporting, that's just administrative stuff basically. But we want to know how often we've submitted things to Skybot. For example, some people ask, well, how do you deal with when a new object is discovered? Do you go back and cut it out, etc.? Well, we do cut them out, but not quickly. We just sort of let things expire. We have our own internal deadline, and then they get resubmitted to Skybot, etc. So this is all tracked in this reporting section here.
Got it. Okay. Uh-huh. Uh-huh.
There's a maintenance section, which I know it's not exciting, but we do think that it's important to mention because it's not really doable without it. All archives, in our experience, I should say, all archives seem to have some corrupt data files and things that may have an issue. There's known issues with every instrument out there, but there are also sometimes that are archive-specific issues. So we go looking for those, and we do some other strange stuff. We make sure that right ascension, for example, isn't 370 degrees or other things that are not like outside of allowed ranges.
Right.
Exposure times that are less than a second, we typically don't worry about those. Some of these might be valid, they could be they're observing Uranus or something like that. I'm not sure. And then we purge data files, so we periodically go through, and anything we're done with cutting all the thumbnails out, everything's done with the rest of the pipeline. We remove those from disk. We don't have the space just to store it. Just as a ballpark, it's about 60 terabytes for the thumbnails alone. So we definitely aren't going to be able to keep the full image frames, which would be like keeping all of Astro Archive. So we don't have to do that because we're just cutting them out. We keep the pieces that we show for the project that we do save and back up. But the original images, since they're available for download again from Astro Archive, we purge those from disk.
Right. Cool. Still, that's a lot of files. Okay.
Yeah, it's a lot of files. So that's the harvest pipeline. We generally run it roughly daily. And so it does stay current. So as we're submitting new batches to folks, they will have data that has become freshly out of proprietary period, or things that were never in proprietary period might be very recent. And so that does make it in there. And people do notice that, actually. People ask about it.
Good. Okay. All right.
Awesome. Well, we're on to the citizen science project. So
okay.
Yeah, we mentioned that we were producing all of these thumbnail images. The original idea was, well, hey, maybe we can look through the thumbnail images and find things that are active. But it turns out there's really way too many of them. I mean, without any of the vetting, I think we were over 30 million thumbnail images to look through.
Wow. Okay.
So that by itself is already too much. There are other reasons, though, to consider citizen science, which is that it's a great outreach opportunity. Engaging the community is fantastic, and it's been shown repeatedly that you reduce bias when you have a number of people looking at an image rather than us that are the scientists, where we're definitely have trouble sometimes seeing the forest from the trees when I'm in there.
Yeah, right.
So there's a bunch of advantages, and our type of project is considered a needle in a haystack type problem.
Right.
And this is something that citizen science is really well suited to.
Cool.
So the basic workflow is we show the image to the volunteer, the same one like that figure one that we showed you, and we ask, do you see a tail or an activity or something coming from the object at the center?
Okay.
We add that little green reticle, just like, a target or something to help identify exactly where the center of that image is.
Mm-hmm.
Um, and yeah, so that's the gist of it. We can go through these individual pieces that describe it a little bit more.
Okay.
We re-clarify here that at present, we're working with dark energy camera data exclusively. We do have other archives that are already pruned and ready to go,
Nice.
but we're sticking with DECAM because it's working so well.
Nice. Very, very.
Um, so as I mentioned before, this is hosted on the Zooniverse platform. This is a very popular online citizen science platform. It has quite the proven track record of success for this type of project out there. So it's definitely, and they're very helpful in terms of designing the project and support throughout. So we really,
Nice.
that was why we went that route.
Good.
We sort of do have a cycle where we prepare the project. And so initially we prepared the project, which took a couple of years. I'll say this was my proposal for an NSF GRFP that was selected, and so that's what that proof of concept went into. So after we prepared this project, we tested the viability with a beta release, which all Zooniverse projects do go through. And we formally launched the project to the public. This was in August 2021. There was some fanfare and stuff, which was actually super helpful in terms of driving classification. And then we get into the cycle that we're in now, where we prepare and upload batches of data, which we talk about in a moment. And we notify folks that there's new data to look at, although people are looking all the time themselves too. So it's people who are quite enthusiastic. And we investigate the candidates from that last batch, the ones that were identified as being possibly active.
Okay.
And so I mentioned earlier, August 2021, the number is a little bit newer. It's a little bit over 10,000 volunteers now. At the time of this writing, it was 8,300. And so you can always see these numbers just by going to activeasteroids.net, clicking on the link, and you can see whatever the newest number is. Zooniverse provides, so right at the
There
front.
we go. Activeasteroids.net. Check it out, people.
Yes, there it is.
Okay.
So yeah, so the project components is the workflow, and the workflow is it's really just boiled down to what I said before. So you look at this image, do you see something that is active or not in the centers? And then when you first get to the project, you're shown a tutorial that gives some ideas. It also sort of tries to help distinguish between galaxies, for example, which definitely can look like comet tails at times.
Yeah. Okay. Yes.
There's also a field guide that's been available at all times, and this is just that describes different things, like when there's donuts, why are there donuts in the image? Well, it wasn't in focus. Or what is a cosmic ray? Because you can get cosmic rays. You name it. If you look at enough of these images, you'll see every possible configuration of image artifact and real event as well. Plenty of galaxies. There is this talk discussion board area as well, which yeah, I don't want to glance over it because, especially in the beginning of the project, but even now, it was actually where our first discoveries came from. I mean, we have this whole system in place. We're going to do this fancy classification analysis, etc. But just within hours of the product launch, people were posting these images in the forums here, which is what they're designed for, and saying, "Hey, I think this looks good."
Cool.
And so, actually, the first couple of discoveries that we made even well before the batch was done, and through this route. And so that's really exciting, and it's super useful, and it's a great way to engage with folks.
Cool. Very cool. Love it. Okay.
So let's see where we're at here in the next part. We're at
subject sets.
Subject set. Yeah, so I call them a batch, but in Zooniverse lingo, they're called subject sets. So this is just a collection of images. And these are the ones that are going to be looked through. There is some art to choosing how many objects are going to be in this batch. So we initially tried 22,000. Because of the fanfare of the product launch, it was done over a weekend, way too fast, at least we thought. So I prepared 100,000. We've since landed at 22,000 is actually a good number. I think our first batch was 10,000, which was too quick. So we have about 22,000, and these are comprised of a different ratio of objects from different classes. So we have main belt asteroids in there, and TNOs and Apollos, etc. And these are what make up a batch. We do now put in some known comets. We initially did not. but we wanted to have some known comments that we had not ourselves classified as a checksum, basically.
Correct. Yes, I'm with you.
So as of this writing, there were 19 batches. I think the volunteers are currently working on batch 24,
Cool.
and yeah. So we do part of the reason for this competition that I should probably emphasize is just that some classes like the NEOs, because they can be trailed, they can look like they have tails when it's just really a trail.
Okay.
So we still include them, but it's a fewer number, and same with the Mars crossers and stuff like that.
Yeah.
Um, we have a way of triaging what we are going to put up there as well within the classes that have many objects. So for the main belt, asteroids are broken down into inner, middle, and outer main belt.
Okay.
The activity is commonly thought to mostly be in the outer main belt. Most of the active asteroids have been found. That's where they've been found to be. And this is in part because the inner ones are thought to be mostly silica based and have less chances of having something with water.
Yes. Follows.
So yeah, exactly. I mean, and they're also closer to the sun, should may already be desiccated.
Yes.
We have a way of doing a very rudimentary metric for saying how close something is to its perihelion passage, in effect. There's the more formal like true anomaly angle, which tells you also whether or not it's inbound or outbound from perihelion. But this is a single scalar here that we can sort by. And so we do front load objects that are closer to perihelion.
Okay. Yeah.
For objects that have many things like centaurs, there's just not that many of them. So we give everything. But for stuff like the main belt asteroids, of which there are over 1 million, we also show objects just once until we get through all of them, which we still haven't done. And we prioritize the ones that are closest to perihelion. We basically are sorting by that. So we are aware that all of these decisions introduce biases. But yeah, there's a great analogy. Henry Shea, one of the co-authors, had given me one time. It's like that box at a game show that someone stands in and is blowing $100 bills around.
Yes.
And they're just like grasping at the $100 bills. That's us in this situation. We've just got so much to work with that we're happy to be in that camp. So we do describe all of these biases here in this work and acknowledge them regularly, but this is a bit of the nature of the game for what we're working with.
Yes.
Yeah, so there's
figure one. Okay.
Yeah, there's back to figure one again. And there's that green reticle I was talking about that just highlights where the center of the image is. It's sort of clear in this particular one, but sometimes when you have several things that are near each other, we had a lot of feedback from folks that they wanted help identifying. This came out during the beta test. And so we're happy to add that. And this image has a bunch of stuff going on with it in terms of that faint tail being there, etc. too. So it's a great image that we like to show. And it's also representative of that contrast enhancement that we were talking about earlier too.
Oh yeah.
So it's we stretch it pretty well. We have an iterative rejection technique that we use to try to get as close to the noise floor as possible, because these tails can be quite faint. People are usually thinking of dramatic comets that you see in the news, but most of the activity that we're looking for is more on this faint side.
Yes, and small.
So there's a training set that we talk about, and this is also came out during the feedback from the beta. So we have a bunch of images that are known to be active objects. So these are primarily comets, because that's where most of them are, but we do have active asteroids and stuff in there as well. And so I've gone through and classified a bunch of images, and this way folks can get feedback while they're doing the classification. So this is something that's universally implemented for us. So if you have a training image that's been randomly injected into your workflow, and you say, oh yeah, I see a tail, then you get this pop-up saying, congratulations, you found activity in an active image. This does decay. So for folks that are classifying many images, they're not getting it all the time. It becomes less and less often that they see it. People do still like reassurance that what they're doing is right and makes sense.
Yes.
So we do leave that in there, and this is all with feedback from the community that this is what they like.
Cool. Good.
We have this very subjective system, which we describe here. It's this expert classification system, it's really like my system that I do for when I'm looking at stuff.
Mm-hmm.
And it's a 0 to 9 system, not in the paper, is because I just want to have a single key to press rather than two keys.
Yes.
Because I've done enough of this to where I've even used like PlayStation controllers and stuff instead of a keyboard, just for ergonomics. It's a thing.
Very
So there's
good.
ways
Very
of
good.
mapping this. And it's important to mention here because this 0 to 9 system, where I say like 0 is I can't even see the object, 1 it's like a point source, and 9 in my mind I call like the coffee table book. Like, this thing is just amazing. You should frame it and put it on the wall. And so
Right.
there's this gray area though. It's in the middle, like 4, 5, 5, 6 in that region.
Yeah. Yeah.
So this is not the same thing as a ratio or a metric for what volunteers say something's active, where we have maybe 15 people looking at an image.
Okay.
I don't remember exactly where we talk about that, but we have we'll show the metric where we validated that 15 is a good number of folks to have look at an image. That was the Zooniverse initial recommendation, and it turned out that to be spot on.
Okay.
So it's not a one-to-one comparison, but you could think of it, if I say that there's nothing there, then we would hope that volunteers are also saying that there's nothing there. So there is some relationship.
Okay.
So we have, I forget exactly how many, over 1,000, I believe, the training images that cycle through as well. So people get a variety of different types of activity.
Good. Good. Okay.
Yeah, so we mentioned that decay already. That's right there.
Yeah.
So both that they get feedback and that there's decay. Some folks ask about, oh, how come this isn't like, kind of do a swipe right, swipe left sort of thing? Because that is something you could do in the Zooniverse app. But you do need to do it on the phone, in a browser, not with Zooniverse app, because we do have these training features enabled.
Okay.
Upon advice from Zooniverse, it was worth the trade-off to have this feedback. People really like the feedback.
Yes, definitely. Definitely. Cool.
Yeah, moving on a bit. Yeah, we have this probability of things to be likely to be active. Yeah, I think we have a more in-depth approach now that's in here in this optimizing classification analysis.
Okay.
And so that's the main thing. That little probability table is actually from Zooniverse. That is their probability of how likely they are to show feedback to, or how likely they're going to show a training image to a volunteer.
Okay.
So a
Okay.
lot of people are curious about this. So just how often do people see training images?
Yes.
And this is that's the exact answer. That's their
Mhm.
formula. They gave us options on changing the formula, but we found that, once again, the Zooniverse experience has paid out, and so this has been a good choice for us.
Nice. Nice. Very good.
So
Second.
yeah, this next part is about understanding the classification. So classification is when someone says yes or no to seeing a tail in an image. So we typically have 15 of those classifications per image, or we had. Things have changed since here, which I'll mention briefly. It can happen that there's more than 15. Like, if two people load their browser at the same time and there were already 14 classifications, then we get 16 because they both submit. And so it's not always an exact number. It's usually greater than 15. We have, since this paper has come out, implemented called early retirement, where if 10 people say yes or
Yes.
10 people say no, as soon as that's happened, we can also retire the image. So
Okay.
an image is retired is the Zooniverse terminology for it's done being classified.
Okay. Got it.
So that's how that works. So anyway, and in here it's always been
Wow.
15. Like I said, we did figure out this little optimization we could do for early retirement that has no impact on the output results. But in order for us to make that decision too, we needed this amount of data in order to justify that.
Cool. Okay. Nice.
Yeah, and so we mentioned this when Snapshot was from 2022 July, and the exact numbers there were again different. This is it's a live project, so these numbers will
Right.
keep changing. But we did have a solid snapshot for developing just for the snapshot for the classification analysis. This piece right here. So the overall paper includes a little bit more than that.
Okay. Good. Good.
So we talk about so initially we just tried this naive assessment metric. So this is what I thought. Oh, we'll just take the number of yeses and the number of no's, and we'll have some kind of ratio, right? If 70% or 100% of the people said it's active, then we'll give it a score of 100%.
Right.
And this seemed like a pretty good way to go. Naively, it seemed like a good idea. And I also thought, oh, well, I'm going to just arbitrarily say if 80% of people said yes, then that means it's worth me looking at, basically.
Got it.
Now, I suspected from day one that this would not be actually the case and that there would be a better way of looking at it. Oh, there's an actual equation for that way of weighting it. That's just a simple, fraction. That gives us our fraction of how many people said, and a given image was labeled. So at the end, we always want our list of images and a score. That's our reduced dimensionality, rather than having a list of images and every single person's unique score for that image.
Okay, good.
This is the goal here. So this is primarily working here. It was done by Will Burris, who's now a graduate student at NAU, so an undergrad at San Diego State at the time. And yeah, if you want to scroll down for a little bit, we could talk about that. There's this concept of a threshold. So when I said if 80 people said yes, that's a threshold that we considered. So we thought that might need to be changed, as well as the weight of the individual score that we're going up in to make that fraction.
Okay. With you.
So this is greatly condensed from a much longer process, but the key pieces that turn out to be important, in I would say no particular order here, really. The first one, it might seem pretty obvious. So how well does someone perform when they're analyzing classification, the training images? So if you look at an image, how well do they do? Are they saying, most of the time they say yes, they see the tail, and there is a tail. As an aside, there were some bad training images because most people never saw a tail, and so that was more on me about taking those out. That happens, yeah. I saw it, but even when I went back to look at it later, I'm not sure entirely what I saw, but this is part of the subjective nature, and an argument again in favor of having volunteers be the ones that are doing this, so we have a consensus. So this is a pretty simple metric right there. So this is going to be a weight, that metric 1, training image accuracy. So if you're classifying training images, you get a bigger weight. And the next one is simply the number of classifications. So this is kind of a common universal approach to saying how expert someone is. Kind of intuitively makes sense. The more you do, the more experience you have, right? Yeah. I mean, you would think that that's the case. It turns out to not always be the case. So we address that. And then the third one, which we call optimism de-biasing, is kind of like the polite term. Yeah, I mean, we also call it a skepticism bonus sometimes internally, but essentially this is a needle in a haystack problem. So we expect this to be low numbers, even with our training images added. So if you see someone is clicking yes, they see a tail 80% of the time or 100% of the time, there's something going on there. Now, some other products have seen this, and I don't think we address this too much in the paper, but a common question is, do you see people clicking yes because they want to get some sort of like recognition or fame or something like that?
I got 100,000.
Yeah, and we don't see that. We do give folks acknowledge they are recognized even if they said no and the object was active. So if they participated in this classification, their metrics still went in there. So I think that's part of the reason why we don't see this as much, is that we don't have that incentive, really.
Good.
Yeah, so we do take into account, so we have a rough estimate about 1% of images to be flagged as active, as worth pursuing. Now, maybe those aren't even all real, but at least we think about 1% of the images are going to look interesting.
Right. Okay.
And so, yeah, we have,
I'm with you.
Yeah, we have these 3 weights, and we also played around with how much the different weights should be weighted, for lack of a better way of saying it.
Correct.
It like maybe this optimism thing is really important for how heavily that's involved, or maybe it's not. If you go back up a little bit, I think there was a figure. Yeah, this one. Yeah, this one right here. So this one talks about, this is just 1,000 images and there's like 10 unique randomly selected users, and sort of their performance over time. And so what we saw is that the vast majority of users do improve over time. Their ability of classifying things as being active or not, like how well they do with the training images.
General trend.
But yeah, which you would expect, but it's not always true. Some people do get worse. Like, so that number 7, so these are all plots with the marker is the number. This is a little trick that I like to do.
Right.
So 7 is one person, and all of this is anonymized, I should say. So I don't know who this is. But this is they do not actually get better with time, at least in that initial window.
Yes.
We do often see that, there's like in that first 10 images, so there's going to be some scatter as
Right.
people are sort of getting their bearings. That's totally fine. So it's a bit surprising though, maybe some people do have a significant decrease over time. So the idea is, in one of those metrics, is that we would like to take someone's expertise as a function of time, and apply that weight as a function of time. This does vastly increase the compute power needed to fit models to how each user is performing with these different metrics through time. But we have found that was worth it was worth investing the time into doing that.
Absolutely. Okay. Cool.
Yeah, so that's that figure there. I mean, it's just 10 of almost 10,000 now volunteers, but it's rare. We talk about how often it happens. It's not very common.
Okay. Cool. Okay.
We should point out too that this general approach we think that other projects could benefit from. So this sort of, we think anything that has this kind of classification scheme going on, these are 3 ways that folks could look at the participation and get an idea of how they could maybe better weight it.
Right. Get to improve the signal coming out.
Yeah. Okay, so I would say that last bit was incorporating the temporal trends there in that figure. So we saw that through time that things can change, and so we do fold that in there.
Yep.
There's some math that describes it. It's a 5th order polynomial that we're fitting, and that takes all these into account. In the end, we come up with a likelihood score for each image. So I mentioned earlier that threshold of 80%. Well, if 80% of people say that it's active, it turns out that actually our weight, I think it's like 0.473 or something like that. So it's actually much less than 50%, which was surprising. But by this metric, that's sort of the magic number. And we did this, we iteratively tested with objects that I classified that yes, they are active, and how many of these do we lose as we change these weights. So that was our end number. So another takeaway for other folks that are thinking about this is that the threshold might not be
exact.
Yeah, it might not be exact. It might not even be intuitive either.
Yeah, it's an empirical weighting.
Yeah. So anyway,
it's just it's like you leaned on Zooniverse's experience, and other people could lean on yours. So
yeah, totally, and definitely every project is unique. And we certainly had a lot of help from folks. Cliff Johnson and Zooniverse, super helpful. Akajita, I mean, a bunch of folks have been really helpful in this process.
Nice.
So there's that threshold we arrive at. If you want to scroll down a little bit, I think so. Metric selection and evaluation. This is how we decided to weight each of those metrics in there. I will say that I don't think I need to jump too much into it right now, but if folks want to read it, they can get into the nitty-gritty of it.
All good. We got candidate investigation.
Yeah, so this is the exciting part. This is like, opening presents every time we have this done.
Yes.
Yeah. So we have a bunch of things that are scored, and so I look through them all, and I use that 0 to 9 scoring system that we talked about earlier, where 0 is can't even see the thing, and 9 it's awesome. It should be like coffee table kind of material, so it looks so active. And so what we do is we as our overview is that we do an archival investigation in all of them. So we don't just look at DECAM. I have another pipeline that looks through a bunch of different archives. They're acknowledged in the acknowledgements later. And we decided to start announcing our discoveries through the research notes of the AAS as well.
Yeah.
And so this was both because we thought that this kind of paper would be a big effort to do, and we wanted to not just sort of like stake our claim on activity, but also give folks the opportunity to observe these objects and do their own archival work, for example, right away.
Yes.
So when we make a discovery, nowadays we bring it to a research note in pretty short order.
Very cool. Very cool. Good. Good.
So if you want to scroll up for a little bit, we talk about it's a bit of a laundry list there, but we talk about the different instruments that are queried through different means. So the Canadian National Local Data Set, the CADC's Solar System Object Information Search.
Yeah.
This is by Stephen Grant, is a fantastic tool that helps us find a bunch of different archives where we might be able to find one of these objects. So in other words, we have a candidate that volunteers identified, and then we want to find everything we can about that one object.
Right.
Everywhere. In addition to that, so yeah, if you want to go down more, there's so many archives in here. They're all very helpful. I should be acknowledging them all. So I then examined those, and we can right there already know, like, this is a discovery, we should be writing this up. But also we do our own observational campaign. So we observe with different telescopes throughout the world.
Cool.
This is the table that describes it. It's worth mentioning. The Apache Point Observatory is 3.5 meter in New Mexico. Of course, we have done follow-up with DECAM, so it's sort of bringing it right back home. Came from there, and then we do follow-up from there.
Nice.
Gemini South has been great, including for some direct discretionary time, which we've been extremely thankful for. Magellan Bod, the Large Binocular Telescope, Mount Graham International Observatory. It's enormous, and it's fantastic. The Lowell Discovery Telescope in Happy Jack, which is with our home instrument, especially as a PhD student there.
Cool.
And the Vatican Advanced Technology Telescope is a 1.8 meter on top of Mount Graham International Observatory, and we've been able to do a ton of observing with that instrument, and it's also just fantastic, and they've been extremely helpful.
Nice.
Yeah, and then we have the ZTF camera in there mentioned, especially for that follow-up.
Very cool.
Yeah, so that's how we arrive at, is this thing active or not, and then we do our actual study of the object itself. So the next bit is the dynamical classification, which we talked about earlier.
Yes.
I would say here's the definition, that histogram parameter. We've got some major axes of bodies. I don't think we should dive too much into it. This is a very commonly adopted metric in our particular area. Yeah, so the main thing is that if it's got a histogram parameter less than 3, it's typically considered cometary, and if it's above 3, it's typically considered asteroidal, like an active asteroid, or sorry, not active necessarily, but a main belt asteroid. It turns out that right around that 3 is a bit of a gray area, and there's things that are tough to put in a box. But this is important because we're going to talk about how we actually classified what we found. So we define, and there are a bunch of cases where there are not widely accepted definitions, including for Centaur. There's a bunch of different definitions out there that folks use. And so we stipulate what we're using right here.
Just however you go.
Yeah, so this is great. So the next part is the fun part, which is the result.
Okay, result. Ooh.
Yeah. So I'm not sure why this is. We should skip to the big gallery. I think would be a great time to do that. Is that figure 4, I believe?
Yeah. Okay, so I'm going to zoom out so we can see it all, and I'll zoom in as need be.
Great. Yeah. So I think this is definitely the main plot of paper for me. So there's 20 panels in here, and each of these represents a discovery made through the project. So some of these discoveries were made during project preparation, and some of them were made after the project launch, but were made about known active objects. So we were not expecting this, but we made discoveries about objects that were already known to be active.
Cool.
These are roughly in some kind of order, so that we've got A through F there are active asteroids.
Okay.
And G is an active Centaur, which is the one that we found. We found that during project preparations.
Let's
And
zoom in.
H, yeah, oh, there you go.
What is
Yeah, and H,
what does the arrows mean? We got three
oh,
arrows.
thanks for asking me that.
Yellow,
Yeah,
black,
so
red.
the green arrows is just pointing out where north is up and east is left. So we, in all of these images, they're going to be, their field of view is 126 arc seconds on the side.
Yes.
Um, for if it's a decam image, it's 0.263 arc seconds per pixel. And we've got the object at the center, and the two arrows that you see there, the yellow and the red outlined black there.
Got it.
So the yellow is the anti-solar direction, and the black is the anti-motion direction.
Got
So
it.
as projected on the sky, so as seen from the ground here.
Yes.
So
Okay.
these are the really commonly expected orientations for tails. So you got the solar wind blowing
Yes.
stuff
Yes.
away, and then also it's just leaving stuff behind it as it moves.
Yep. I'm with you.
Comets though are fun, and they can do whatever they want
Strange
sometimes.
things.
So they're
Yes.
not. Yes, they are, and so they don't always do what you expect, and that's fine.
They can outgas in strange ways.
They definitely can.
Very cool.
So I think H through L are the quasi Hildas, and then the remainder are Jupiter family comets.
Yeah.
And so each of these
Nice.
is an image. I think we have 16 discoveries, so previously unknown active objects from
Very
the
cool.
project. So four of these that are in here were already known. A couple of these were made during project preparations, but the majority of these are the subject of this paper, which is the discoveries made by the
Very
project.
cool. Very cool. That's
And you get to know these very well. That letter R there was actually one of the ones that was identified by Talk right away in the chat forums there. So we were just no, sorry, that little letter R, the 2017 284.
Oh, okay.
So we've got a couple of those, the 20, yeah, there were, then the one to the left of it as well. These were found by Talk right away.
Cool.
And there, the 2005 Extra 132 turns out to have already been known to be active, but we found additional previously unknown activity for. Yeah, so this is the main gallery.
Beautiful.
If you want to go back to the text, that would be great.
I think I'll just stare at this figure for a while, but
Yeah, I'm pretty happy with it.
Okay, so we have results and
Yeah,
the dynamic.
so I think this figure here, which is referring back to the dynamics part, one of the challenges I mentioned that the quasi-Hildas are a little bit more difficult to identify. So we do have to do dynamical simulations to figure out exactly what they are, to tease out the different bodies. So these are 6 representative Jupiter co-rotating reference frame plots. So in each of these, there's like a little orange squiggle on the right there.
Yes.
That's actually Jupiter's motion in its orbit.
Yes. Yes.
And then the rest of them are the solar system object orbit around the sun.
Doing.
Right. Yeah, and so
very
like
cool.
there's a comet which is just simply going on its way in. It's doing one or the other, and the main belt asteroids you can see are constrained to a certain region, and they're kind of nice, well contained. The Jupiter family comets you see are crossing the orbit of Jupiter, which is that tiny little orange line there.
Way over here. Blow that up so people see it. This one right here.
Yeah, each of these has a little orange line, which is Jupiter in its orbit, and it moves in and out, of course, with respect to the sun as well. But these are all staying on that co-rotating reference frame perspective. And then the piece that's helpful here is that you see Hilda. That's actually Hilda itself, which is 153, I believe, Hilda. And so you see this tri-level feature. So this is different than the Trojans, which are leading and trailing. This is the third point. And it's so the quasi-Hildas, we see similar tri-level features, but they're processing through time. And so it's typically different than the Jupiter family comet, but so we often will diagnose both with the orbital parameters as well as this plot here to help distinguish between quasi-Hilda objects and Jupiter family comets.
Yes. Okay.
Yeah.
Okay.
And so there's a corresponding plot for that gallery that show the 20 co-rotating reference frame. So I think it was at maybe figure 5 or figure 4. But it's like the equivalent of the gallery, except with the co-rotating reference frame plot for each of the objects.
Let's do 5. Here we go. Oh, nice. Nice. I get it now. Okay, good. Good.
Yeah, here we go. So it's and even just looking at this plot, you start to realize, oh, you can see how they're grouped, just on their own.
Yeah.
which is we find to be super helpful. That 2019 0831 is a very strange object. It kind of fits into almost anything, but you can see the little loop-de-loops around Jupiter. That's because it
Yeah.
had a really recent close encounter with Jupiter that really
Woo,
altered its
woo.
orbit. Yeah.
Yeah, look at some of these. That's hilarious. Okay.
Yeah, it reminds me of like spirograph when we were kids and
Exactly.
stuff. Yeah.
Yeah, but their orbits, so very cool. Very
Yeah.
cool.
But they're very helpful for understanding the orbits of different bodies for sure.
Absolutely. Absolutely. Well, they also give you predictions too, like maybe you caught it when it wasn't necessarily a perihelion or something. And so this gives you if you're going to go back and look again. Nice. Okay.
Cool. Yeah, I think we can if you want to go back to the results section.
Sure. Let's go back to the results. Let's go here. Bump, bump.
No, it is a long paper.
Uh-huh.
It's 24 pages, I think.
Yep.
Yeah, great. So if you want to scroll down a little bit. So yeah, that we talked about here about the pre-launch discovery. So I already mentioned that proof of concept. That's the first section there, the 2000 SY-178. GALT was an object that we found to be active. It was our first time of using our archival investigation technique to find that an object had actually been active before, which was super useful. And we've had a number of results since then. So the project was originally designed to find new active objects, previously unknown active objects, but we've also made a bunch of important findings about objects already known to be active, and so that's a good case there.
Good.
Next up should be the
Active centaur.
yeah, so 2014 OD392 now with the C/ for Pan stars. So this is our one and only active centaur discovery so far. We have some that we're still pursuing, but this is our active centaur discovery. Yeah, very happy about this.
Nice.
And also represents our first new active object as part of the project. So this was again a part of project preparation while we were testing out the thumbnail cuttings and all that kind of stuff, and that's when this came out.
Popped out during testing. Lovely.
Yeah, and it's and each of these papers also has a technique that has been folded into the grand picture of this paper. So the GALT one has this observability concept where we consider observational biases and the temperature of a body through time. And so, yeah, there's too much really to get into for each one. That's why we're referring folks to the papers, but we do provide a synopsis here of each of these objects.
Very cool.
Yeah. 433P, this was another case where folks found it's a main belt comet. We were able to say it's a main belt comet because we found previous evidence of activity that indicated it was sublimation driven, and being active more than once is also often an indicator of sublimation driven activity, especially if it's when it gets closer to the sun. Although not always the case. GALT is a case where it has been active multiple times, and it has nothing to do with how close it is to the sun. Right. So it's thought to be a rotational disruption.
Okay.
Yeah. So moving on, I think after I said 2005 Q173, it's now been renamed 433P. This is the great thing. Solar system names, they keep changing. Yeah. So I think after that should be 282P is mentioned maybe at the top of that page there.
Oops, sorry.
Yep. Yeah, and that was a pre-launch, post-launch discovery. So that was our first. This was volunteers found an object that was known to be active, but they found another instance of it being active. Good. And so we also led us to reclassify this object as a quasi-Hilda, and we were able to do observations with Gemini and do a study of this object, which was great. And I think that also represents our first post-launch peer-reviewed publication.
Yeah.
So the active asteroids discovered by the project are all described in here one at a time. We give the orbital elements and some other pieces. Some of them, like that 2007 FZ18, we only had one image of it being active, but it's a great image. There's a tail in each of the directions, and there's some really wonderful images in here, but most of them we have multiple images of. That's the one exception. And some of them, such as that 2010 LH15, it was that we found more than one epoch of activity, so more than one orbit where it had been active. So that one's a main belt comet. So I think we've discovered something like third or a quarter of all known main belt comets now through this project.
Cool.
So these are really significant increases in the numbers of known objects. Yeah, it's super exciting.
Very nice.
Glad that it actually worked, right?
I'll actually ask a question. So I'm curious. So can you put some percentages on, you know, how many images to how many new discoveries of active asteroids? Is it like 1%, 0.1%?
That's a great question. I mean, I think I would have to look, you know, these, I mentioned earlier, there's a ratio of the makeup for each of these batches of how many.
Right.
But you know, off the top of my
Yeah.
head, I think it's maybe 1 in 10,000,
Okay.
something like that.
Uh-huh.
Yeah.
Uh-huh.
So it's, which is not that different than what's been predicted. That we did a study in that proof of concept, and some other studies have done it. They estimate about 1 in 10,000
Okay.
maybe asteroids should be active. So another way you can look at that is that there should be 100 of these things out there.
Yes.
And so we've found a number of them, which has brought that number up to about 20. So there should be more that we can find too.
Very good. Getting our way to completeness.
Yeah.
Very
We hope
cool.
so.
Very
So
cool.
yeah, and then we talk about, so that was the active asteroids category, which was the sort of the main one we were after.
Right. Right.
There's several other objects in here. Each one of them has sort of, they're all unique, interesting characteristics. And some of these are coming back, like 2015 FW4 and 2. Now's the time to observe it. So we're very excited to see it reactivate, for example.
Yeah.
The quasi-Hilda objects, there's quite a number of these that were in here.
Yeah.
And so I think that's about a third of the known active quasi-Hildas we've identified. So a quarter, a third, something like that. But a significant number compared to the number of known active quasi-Hildas.
Significant increase.
And then the Jupiter family comets. So this is a bit of an unusual category in the sense that, you know, it's already got comet in the name of the category, so it's not super unexpected in some ways. But there's many objects that are discovered that have this Tisserand parameter in the range you would expect to find for Jupiter family comet, but they've never been seen to be active.
Okay.
So it's highly surprising that we would find some to be active, but it is exciting that we're finding them because they are understanding. They're important to understand these bodies for a number of reasons.
Absolutely.
For one thing, is they have the potential to be impactors on Earth, and they're also easier to study. They're short period, and they're around more than the long period comets.
Very good. Okay.
And so we described a bunch of those in there, and there's a couple that are currently active, like a 2012 UP192. So each one of these, as I mentioned, we mentioned there's a note too, so people can also refer to the note if they want to see additional images, for example.
Oh yeah, the research notes.
Yeah, those would be in there. We just originally tried to have all of the images that we could in here, and it was just way too unwieldy in the paper. So yeah, but there's images for sure.
Beautiful.
So in terms of the those are the discoveries. To me, that's the most exciting part. But we also talk about their classification metrics. This might actually answer your question too a little bit better in terms of, like, here's how many asteroids that were examined, how many volunteers said yes, and so subject versus objects, I should say. So you can have a subject as an image, so you can have multiple images of the same asteroid. So objects means unique objects. So it's almost the same for asteroids because we've been mostly showing them after about batch 3 or 4, we started just showing them once. We decided we want to go through all of them before we show someone the same object twice.
Back, right.
Yeah, even though the object may be somewhere else in its orbit, might be look better for chances of getting activity. And so that's the number of discoveries. So, 6 out of 240,000. It's not inconsistent. It's what we thought it would be, roughly.
Right, 1 out of 100,000, just about, or 10,000. Yep.
Yeah. We're astronomers. We can say orders of magnitude.
Right. Sorry, I made a verbal there. Oopsie. Oh well.
No.
Okay.
So Yeah, so that's the meat of the metrics for what's been examined. You can tell obviously, for example, there's far fewer Centaur images available. I mean, they're further away. They're
Mm,
inherently they're going to be fainter as a result,
there's just less,
and so there's just few of them to be looked at.
but you got one.
We did get one, yeah. So that's table 2, and table 3 there shows the activity circumstances. So for the activity
Ah,
crowd, people want to know when it was active during its orbit, especially the
yeah.
true anomaly angle says whether or not it was before it passed perihelion, so was it inbound to perihelion or was it outbound to perihelion.
Yes. Okay. Okay.
Um, so people like to use this, this is an important update here because people want to know when they're going to go observing active asteroids, when do they have the best chance of it actually being active.
Right.
You know?
Good. Observatory planning or observation planning.
Yeah, yeah.
Okay.
So yeah, if you want to go on to the next one, I think we're at
Discussion
yeah. So we've got
or
yeah, we do talk about there's another key point here, just sort of talking about the center activity occurrence rate. This hasn't been done very much because the numbers are so low. But we do talk about that in here.
Mhm.
So I think that's so we found this to be about roughly 9% of them are active, which is a really high fraction for compared to
the other ones.
asteroids or something like that.
Yeah.
Yeah.
Mm-hmm.
And it's a little bit of a revision from what was previously thought, which was about 13%.
Okay. Okay.
Um,
Yeah, you got 9.
yeah.
Uh-huh. Uh-huh.
With the disclaimer that the definition of centaur, it does depend on which definition you adopt, but
Yes, numbers will
that's
depend on your
yeah.
definition. Uh-huh. Okay.
So we also had this yeah, so in the discussion part we talk about the agreement between the volunteers and experts. um,
That's an interesting question.
yeah, so we showed that in that table earlier, sort of the objects, what they
Mm-hmm.
had classified as being active versus what we had classified.
Mm-hmm.
um, and so we flagged of that 2,700, we flagged 258 of them as being worth following up. As some of them we could pick out right away as like, oh, this is definitely a galaxy. So the kind of things that you probably need to be an astronomer to be able to recognize some of these image artifacts.
Yeah.
But what did survive was actually still a very high percentage, so we were quite happy with that.
Yeah.
Um,
Yeah.
I think, needless to say, before we launched the project, there was a lot of concern. Can the public even do this at
You can
all?
do
Is
this.
it even
Right.
viable? Yeah,
Right.
but right away we saw the slope that most people were saying no, they don't see activity, which is what we hope because it's not there most of the time.
Right.
And people were able to see activity in the training data, so
Very
this
good.
just sort of validates that. But the overall number of a fair amount of these being candidates that we follow
Very
up
good.
is fantastic.
Yeah. It's actually pretty good numbers here. Very cool.
And you also get an idea if there's 16 or 20 in this paper that we must be still investigating some of these because there's more on that list.
Yes. Okay.
Um, so yeah, that classification rate and completeness. So this is
Wow.
a special. Yeah, people want to know this for a bunch of
Wow.
reasons, but one of them is thinking about upcoming surveys like LSST.
Mm-hmm.
So the meat for us in understanding this here is that we can get caught up. We can examine all of the known DECAM images as well as examine all of the incoming new images that are being taken.
Yes.
It would take a number of days to do that. We mentioned earlier that automated vetting too. So even if we take into account all the vetting with everything, it would be possible to eventually catch up.
Eventually.
Yeah, I mean, in a few years. I mean,
Okay.
it's fine.
Okay. Okay. So it's
Yeah, I mean, we may not need to do that, and we may not want to exhaust all of the image data either. We may decide to work with some other archives first, where we have some maybe lower hanging fruit. That's sort of
right.
been part of our MO, and we
Cool.
like to keep it interesting, for folks too.
Yeah.
But it has circulated a little bit out there. You sometimes hear folks talking about citizen science as a panacea, and that we can solve all of our future problems. And it may not necessarily be true. So we talk a little bit here about LSST. So LSST, this is an upcoming survey. It's an 8.5 meter class. It's going to be in Chile, and it's going to be 1,000 images per night with 3.2 gigapixel camera. So that's 100 terabytes of data per night.
Yikes.
And it's really the numbers are high. So in a single it's a 10-year survey, but even just thinking about sort of nightly output.
A night,
about 5.5 million minor planet detections. So that's a lot. So that's about 8,000 per image. And for context, that's roughly like an entire night of dark energy camera, and then they're going to be doing that 1,000 times a night. So that it's really a lot more data and several orders of magnitude. So if we look at this number down where it says like default targets vetting in there, if we can do this aggressive vetting we're doing, so there's no object in the middle, and it's going to be too faint, and based on the depth, if we can cut down everything, it still leaves an enormous amount of data left to do.
1.2 million.
Yeah.
Yikes.
So one night of LSST data at our best rate of classifications, the most people participating would take 150 days to look at that.
Right.
So we said it's clearly impossible. So I did mention that we're sorting by object proximity to perihelion. So we want things that are closer to perihelion, more likely to be active. Obviously, there's the bias that you won't know if things are active when they're not near there if you're not looking at them. So we talk about ways we can consider that more, as well as to have harsher restrictions on the delta magnitude limit, so that you need to have things be a lot brighter than the background.
Yeah. It's sort of that's the low-hanging fruit, right? Put enough cuts on so that the volunteers will generally find something. Okay.
Yeah, and
okay.
Again, thinking of we do want the low-hanging fruit. We want the harder to find fruit too, but we do want low-hanging fruit. We want to keep everyone engaged too. If we're never finding anything, it's not super exciting.
Fun.
But yeah, so I think the point there though is just that we will need to make some drastic cuts, and one of the ways I think that we'll be working toward that is through AI. We do have something that we're working towards.
Yeah,
we have a couple notes out about that, but that is we always need to mention this with citizen science. It is not why we have the citizen science project. We are not trying to just train something that's going to do their job or something like that. We don't think that was possible. If it was possible, we wouldn't have gone this route in the first place.
Correct.
But we do think that it's we have evidence that we can sort of help make an assistant that helps us do more vetting to get rid of definite garbage.
Right.
Things that are definitely inactive, and so that is something that would be able to help with something like the LSST scale project. I also, in the practical considerations there, it's kind of a little bit can be tough to come up with numbers for what does a project need to work in something that's the size of LSST. Sorry about that.
Right.
And the answer is it's the figures are in here, but it's about 100 megabytes per second of transfer rate, and we need about 4 terabytes bandwidth, temporary storage. And so yeah, it's doable, but there are some pretty heavy requirements, and this is on a daily basis. And so it also requires a lot of things always be working, for example.
Technology, it always works. What are you talking about?
Yeah, exactly. What could go wrong? So
what could go wrong?
So this may be of use for folks that are thinking about if they want an image-based science platform, for example, or a system where they would be training machine learning and having things go up to the Zooniverse project. This gives some actual hard numbers that folks could use. Yeah, and we talk about the end results in terms of what 100 CPU GPU pairs at a rate of 100 per second. That's a lot of CPUs and a lot of GPUs. I mean, that has a price tag on it typically.
Yes, it does.
So it's a significant amount. And so we mentioned their AI vetting would probably help. I'm very excited about this project continuing into the LSST era. We absolutely are thinking about it. When I created the project, we were thinking about it in our initial proposal. And so we definitely plan to be ready. We're excited about it. We're not saying that it's not going to do anything, but we do want to set some expectations in terms of the amount and the volume of data.
Right. Right.
Yeah.
Where
And
does
so
it
that in that
result?
so yeah, that project outlook there, that is thinking ahead about it. We certainly are making a lot of discoveries now. They're in this paper, of course. We've already had a couple more notes come out since this was published. Those were both actually AI related discoveries through the project.
Okay.
And so yeah, things are definitely still moving forward. And we encourage folks to visit activeasteroids.net and click the link to get started. It's always there. Anyone who's able to participate, there's no special skills or anything that are needed. It's ready to go. Yeah, and just this in this recap, we've made a bunch of discoveries, 20 discoveries that are in this paper. 16 of these are previously unknown active objects. And we've got this NASA partner program is exciting. Folks love participating in anything that's NASA science. It's on the Zooniverse platform. And I gave some updated numbers earlier. It's already past 10,000 volunteers and over 8 million classifications of over 600,000 images. We've got some metrics there to talk about the techie side for folks who are interested in the amount of storage, et cetera, that's used. We talk about our classification analysis, which is pretty novel, and we do think that other folks could use it for different citizen science programs. And we reiterate that we really like this paradigm of citizen science, and it's really working well. I mean, it's very cliched, like, you know, you can leverage this paradigm for engaging the public in a scientific goal, and it's true. This is showing that it works out quite well.
Cool. That's so great. And
then we mentioned our follow-up observing there, and we're extremely grateful for all of the observatories and the telescope time that we've been given. We list all of our new exciting discoveries and links to the research notes and other places as well. There's a couple of these also have their own papers. There's 2009 DQU 118 from the Oldroyd. Exciting stuff.
Wow.
And yeah, some disclaimers that the metrics are still preliminary. I would say that that's true. And we talk about, yeah, so there's that specific question you asked of the asteroid found 25 or 0.01%.
Yeah, there we go.
We're candidates. Yeah.
Okay, thank you.
Yeah, and then these are all in line with the existing occurrence rate estimate, about 1 in 10,000 asteroids being active. And you know, after that, we identified 5.7% of the centaurs being active, so occurrence rate actually at about 9% overall when we consider all of the discoveries that the field has made.
A little bit more. That's awesome.
Yeah, it's very exciting. And then we have our quasi-Hilda discoveries, and yeah, that's it. And then I would be remiss if I did not acknowledge our citizen scientists, in addition to the co-authors that are mentioned before, but we also have a lot of effort from individuals who examined some of the objects that are in here, as well as super classifiers. Elizabeth Baton of Belgium is our project, our forum moderator, and she's been absolutely instrumental in our project success.
Thank you, Elizabeth. Very cool. Very cool. And this article has an awesome acknowledgement section. I invite you to go.
It's only like 4 pages or something.
Only 4 pages of acknowledgements.
Yeah. Yes. Yeah. That is the world we live in. Yeah. So that's the paper. I mean, thanks for letting me go through it with you.
Yeah. Well, thank you so much for walking us through your very lovely AJ article. That was awesome. Yeah. So you mentioned it a little bit there toward the end. And let me just push on it, particularly since it's sort of in the title. Where do we go from here, given the published article? Will there be a second edition of this paper, and second results, and so on? And just sort of, you know, where do we go from here, given the published article?
Yeah, we're definitely, we have more work already in progress. We had a nice dividing line for what would be going into this paper, and then we've had discoveries since then, which will be coming into another another paper. I mentioned briefly we've had some AI momentum as well in terms of
Uh-huh.
creating an assistant for the project, and so
Cool.
we have a paper that's coming up that'll be about that and include several more discoveries along the way. And you can always keep an eye out for research notes that we're putting out as well about discoveries. Um, we'll be seeing more of those, and then of course the project is live and ongoing, so you can you yourself can go and participate. Everyone is welcome. And you can always just check out and see what the project is doing by
Yeah.
checking out that site as well. There's a list of results. There's stuff about our team on there. Um, it's really exciting. I mean, it's been very fruitful, and we expect it to continue to be fruitful. So
Yeah.
moving
Well,
forward to that.
congratulations on getting this one going. I think it's really awesome. So
Thank
yeah,
you.
really great. Yeah, very, very happy. And I really look forward to seeing this develop over the next couple of years, particularly as LSST comes on and you get your pipelines down, you get your eye rolling or volunteers. It'll be really exciting to see this grow in the next couple of years. Very nice.
Yeah, we're really looking forward to it, and we're very excited. Everyone's very excited.
Cool.
Yeah.
Thank you, Colin. And
Yeah,
that will
thanks,
do it,
Frank.
everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.
Thank you.